Welcome back to your AP Calculus BC Topic 2 Series Convergence Tests unit. This is our second to last lesson in this unit. We are on our very last test as well. So you're like, wait, are we done with tests? Why do we need the next day? The next day just goes into a little bit of extra information, but it actually relates very closely to today. So without further ado, I bring to you the alternating series test and the alternating series error bound. So, opener. Graph the first 10 partial sums of the series and record the graph below, then approximate the sum. Oof, there's a decent amount to do here. I'll let you guys decide how you want to do it. Once you're done, I will show you a way that I'll probably do it as well, and then we will go from there. Ready, set, go. All right, so I'm assuming that you are done at this point. If we're looking for partial sums, there's any number of ways to do this. I think there's maybe no real easy way, though. There's probably a way, I guess, we could change our limit of summation up here. I'm just going to give you one way to do it, though, and that's going to be through Desmos. I think this will probably be the easiest way to go through it. You could also do this on your calculator. It's just easier to change various things on Desmos. So we're going to do, I was hoping I could type in sigma, but there's probably a shortcut there. So I'm going to go ahead and pull up a function, miscellaneous function, and my sigma here. We're going to go from 1 up to something. We'll leave this something blank for this point. We're going to use our first formula, -1 to the n plus 1 over n. So we'll go over n first, and we have -1 to the n plus 1, nope, need parentheses, always forget, n plus 1 over n, love that. And then let's just go from 1 to 1. Okay, well that's 1. So we can kind of keep a running tally here, right? So my first point is the point, and I'll just keep the tally down here. We have the point 1, comma 1, and there's my first point, yeah? All right, my next one is going to be up to 2. And so that gives me the next sum, which is 1 comma 1/2. Right, nothing bad. And I'm sorry, we used 2 here, duh, because we added up the first 2 terms. And then we go 3, and you guys get the idea. In fact, maybe I'll just call this A, and I'll add a slider. And then let's even go step up by 1s. And we'll go from just, say, 1 to 10. That should give us the first 10 terms pretty easily. So we already did that. There's 1, there's 2. Here comes 3. So this one becomes 3. Actually, I should probably do this up above, otherwise I'm going to run out of room pretty darn quickly. So we get, no, that's not what I wanted. 3 comma 0.833. Okay, and then my next one is 4, and I think we get the idea at this point. Of course, I still apparently don't know how to press enter, so life is tough. 4 comma 0.5833. Cool, and then we have 5, and so on and so forth. Now, as you look at those points, you can see that we are really alternating back and forth over something. And remember, these are the sums. So first, I think the sum is 1. But then because of the negative up here, I have to subtract 1/2, and that brings me down to 0.5. And then I'm going to have to add 1/3. That's my next term over here, and so on and so forth. I think we get the idea. We're adding a bit, and then we're dropping down. Then we're adding a bit, and then we're dropping down. So let's see. Let's do one more here. I don't think we need to do too many of these. And we get something like 0.61666, something like that. And we can see that we're oscillating back and forth. Now, I'm going to go ahead and throw all of this in a folder so that we can hold on to this and come back to, actually, I don't want this guy in a folder, though. I really just want all my points in a folder so that I can turn them off and on again when we compare these two series. Second try. There we go. Technology never works the way you want it to work. Now does it? Perfect. These are all my extra spaces from hitting enter, because apparently I know how to work a keyboard, and it looks something like that. Cool. So then I'm going to drop this folder down, and we're going to say, we'll call it series 1. from the opener. So I'll turn all those off, and then we should probably do the same thing for the second one, which is just 1 over n. It's not negative 1 to the n plus 1. Very, very similar, but 1 over n. They did ask us to approximate the sum, but we'll do that after. So first point is going to be 1 comma something, and we find that by going 1 over n, and we're going to sum it up from 1. 1 comma 1, that seems pretty familiar, not a surprise. Next one's going to be 2 comma something, so we add up the first 2 terms, so it's 2 comma 1.5. All right, we don't need that extra parenthesis. And then we have 3 comma something, 1.8333. 4 comma something is 4 comma 2.0833. Very nice. 5 comma something. We'll just maybe do 2 more here. Oh, you stopped that. I told you to go up to 5. There we go. 2.2833. And we'll do one last one, which is 6. And this one is going to be 6 comma 2.45 exactly. That's exciting. Cool. And so we end up with the series here. Okay, that's looking pretty darn good. I'm going to add in one more folder so that I can toggle this series on and off again, because we're going to be referring back to these a decent amount. So I'm going to go ahead and drop this one down. We'll call it Series 2. We'll turn that one off, rearrange so it makes my heart happier, and we're good to go. Okay, so we have my first series, and that was the one that added, then subtracted, then added, then subtracted. Looks something like that. Looks like it's bouncing back and forth. Versus my second one, which just is going up and up and up. Now, we should also know that this second series is the harmonic series, and we know that the harmonic series, even though it looks like it's increasing, maybe even to an asymptote, right? It's curling off. It actually doesn't increase to an asymptote. It increases without bound. The partial sums never actually approach a specific number. We don't know too much about this guy down here. We're going to name him later on, but we get the idea, I think. So we're going to get rid of these two, don't need them anymore, and we'll see what we can do. Compare and contrast the series. We did that. They did ask us to approximate the sum. So maybe if I look at that first series, it looks like turning it on, my sum has got to be somewhere in between like 0.6 and 0.7. Maybe that's 0.8. So somewhere between 0.6 and 0.8. I mean, it's bouncing back and forth, has to be there. And we know we can't approximate the harmonic series. I guess I should have named it that way. The harmonic series, because that diverges, so it's not actually going to sum up to anything. Okay, let's get to it. We should note that the series B from the opener, as mentioned, is the harmonic series. However, Series A is almost identical to Series B, but because the signs alternate, maybe I should have written out what's happening here. If you substitute in 1, this becomes a positive up here, and we get 1 over 1. When we substitute in 2, 2 plus 1 is 3, negative 1 to the third is a negative, so it's negative 1 over 2, and then we alternate like this. Right? And so what I was doing when I added up the first 5 terms is summing up all of those. When I summed up the first 6 terms, we did all this, so on and so forth. And if we compare that to the harmonic series, extremely similar, except instead of those minuses on every other term, we have positives all the way through. So if the first series, or the part B series, is known as the harmonic series, then it probably is not going to surprise you that because our signs alternate, then this is known as the alternating harmonic series. And I have no idea why this is here. This comes in later on, that AST, but this is not the AST. So our last test for convergence is extremely easy, arguably the easiest of tests. It is often known as the alternating series test. This is abbreviated the AST. So if someone says this series converges because of the AST, that's what they mean the alternating series test. Nobody abbreviates the alternating harmonic series. Maybe you could get away with AHS, but that's very uncommon. So there are only 2 criteria that need to be met for the alternating series test to prove convergence, and let's take a look. An alternating series is in the form of something that alternates in sign. Almost always that will be negative 1 to the n or negative 1 to the n plus 1, but we will see an example of something that doesn't quite fit that pattern. But either way, there's going to be this alternating factor that's multiplying in somehow, and then there's going to be an actual sequence at the end. Okay? This alternating series will always converge if eventually this sequence becomes decreasing. And I say eventually in quotes because really there's going to be a finite number of terms. Maybe the sequence kind of goes up for the first two, but as long as it starts to go down eventually, then we count that as, and really we say non-increasing because it could either be decreasing or constant. But eventually, if the terms of a series are non-increasing and the limit of the series goes to 0, and you're like, well, or the sequence goes to 0, and you're like, duh, that's the nth term test for divergence, then our series converges. That's it. So easy, so quick. There are two notes here. The AST only tells if a sequence converges. So if these aren't true, it doesn't mean that the series necessarily diverges. You can't conclude and say the series diverges because this doesn't work. You need to conclude some other way. And honestly, the most common way is when you do the nth term test for divergence. That guy right there, and that's what they're saying right here. If that doesn't equal 0, then use that as your justification. Because the nth term test for divergence isn't equal to 0, then the sequence diverges. Easy enough. I always suggest performing the divergence test with the absolute value of the series because ultimately the absolute value of this series is just a sub n. It's going to cancel this out, but again, we'll see an example of that shortly. So let's take a peek. A couple of these quickly. Determine whether the following series converge or diverge. Well, looking at this guy, and actually, well, we should jump back up to that in a second. Well, maybe we should even do it right now. I have some space on this page. I really wanted to actually discuss the convergence or divergence of the alternating harmonic series first. I think that probably seems most important since it's very similar to the harmonic series. So let's start with that. So we're going to go from 1 to infinity of -1 to the n plus 1 over n. And really, my series would look something like this. I would say first we're going to find the limit as n approaches infinity of the absolute value -1 to the n plus 1 over n, which of course the absolute value is just going to strip away that alternating factor. It's just the absolute value of -1 is just 1 over n. And once we've stripped it away, we really don't need the absolute value either. And of course, we should be comfortable 1 over infinity is 0. Great, that's it. We're done. Right? So you can do a nice full conclusion here. You can say something like as 1 over n is decreasing. It's always good to state the criteria here. So not a bad thing. As 1 over n is decreasing and the limit as n approaches infinity, you can just use 1 over n. You can use the absolute value. Doesn't really matter. And I'll do this. Equals 0. Then as the series is alternating in sign. And you should probably prove that to yourself if you write out the first couple of terms. Does it go plus, minus, plus, minus, or minus, plus, minus, plus? It does, though. We've seen that already. Then the AST, Alternating Series Test, proves blah, 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 n equals 1 to infinity, -1 to the n plus 1 divided by n converges. And that's it. Very, very quick. Basically, does the limit become 0? Does the series alternate in sign? Awesome, you're good to go. Nothing bad. So let's look at a couple more of these then. Okay. Similar idea here. I'm just going to check each of these really quickly and I'll leave the conclusion up to you. It's nothing too bad. I always start with the absolute value of the whole series, which again is going to take away that alternating factor, and then we won't need the absolute value anymore. That's 0. Great, it's 0. Therefore, the series converges. Easy. Again, we should do a conclusion. Decreasing, 0, alternating in sign, alternating series test proves convergence. Nifty. Okay. What about something like this? I think probably formula first, guys. So we go from n equals something to infinity. This is, what's my pattern? In the numerator, and I'm going to leave some space for that alternating factor. In the numerator, we're going up by 1, so we know the slope is 1. And then if we try substituting, let's just do 1. If we substitute in 1, 1 times 1 isn't 2. We need to add an extra 1 to it. And in the denominator, 1 times 1 is 1, so I think we're set. The only thing we didn't account for was the alternating factor. Negative 1 to the n, try that first. But if we substitute in 1, this becomes negative, and the first term is not negative, so we should probably do the n plus 1, and then we're good. All right, and maybe we should put this whole thing in parentheses here. So let's go ahead and try the limit as n approaches infinity of negative 1 to the n plus 1 times n plus 1 over n, which is the limit as n approaches infinity of just n plus 1 divided by n, which using dominance is the limit as n approaches infinity of n divided by n, which is just 1. Uh-oh, we are not going to 0. So this series will diverge. And so what do we do with this? We'd say something like, as the nth term test finds a limit other than 0, the series diverges. And I'd be a little more careful about my wording, but we get the idea. We've done this a million times at this point. Okay, really today is just a nice little limit practice, at least for the beginning, right? We're just understanding that the alternating series test is a pretty darn easy one. And I think that's really all there is to say about it. So natural log of n over n, which one is more dominant? Well, n is more dominant in infinity. Natural log is our least dominant out of all the functions we study, and so we get 0. Great, it alternates in sign, therefore converges. Last one. Well, this one's kind of weird. Is this actually an alternating series? I don't even see a negative sign on here. Let's try the first couple terms, right? Let's try, and I'll add these up and then simplify after. Here's when n is 1. It becomes 1 pi divided by 1 plus cosine of 2 pi divided by 2 plus the cosine of 3 pi divided by 3. And let's do one more, cosine of 4 pi divided by 4, and so on and so forth, right? So is that alternating in sign? Well, maybe we should simplify this. Cosine of 1 pi is actually negative 1, I think. Cosine of 2 pi, cosine of 2 pi is 1. Cosine of 3 pi is negative 1. Cosine of 4 pi is positive 1. Look at that. Isn't that exciting? This is actually a form of the alternating harmonic series. They have put the negative out here. So if you wanted to make it look exactly like the alternating harmonic series, you could factor out a 1 from here. Our alternating and harmonic series always start with a positive term. Or at least more commonly is done with a positive term, but a nice little trick there is that you can factor out a negative and see that this is the alternating harmonic series. And yes, you can just say this is the alternating harmonic series, therefore this converges. So it's kind of weird, right? The harmonic series, not alternating sign, does not converge. And again, I'm not even sure if we discussed this, but the reason that the harmonic series doesn't converge, even though this goes to 0, is because the terms don't get, air quotes, small enough, end air quotes, when we're adding them up to actually not add to, or to actually add to something. They don't approach 0 fast enough. However, as soon as we make this alternate in sign, then it gets closer to 0 really twice as fast, probably even more than that, because then we start adding and dropping value much, much quicker than if we're just adding something up. All right, now that's all we really need for the alternating series test. Now we're on to the alternating series error bound. This one is actually not much more complicated, but it's the first error bound that we see this year. We will see 2 error bounds total, one this topic, one next topic. But I always like introducing this early on because I think it's very understandable at this point, and there's a nice little graphic, and it ties so well into the alternating harmonic series. So we're going to go ahead and use a number line to graph the progression of the first 10 partial sums, beginning with the first partial sum of 1. So my first partial sum was right here. That was 1. And actually, I'm going to jump back to Desmos here and expand my, we can rename this now. This is now the alternating, if I could spell, alternating harmonic series. Okay, looks like this. And we're going to try and see if we can do both of these at the same time, and I think we'll be pretty successful here. There we go. We'll zoom out a bit. Nice. Okay, so my first term, rearranging slightly, was 1. My next sum, oh, you stop that. My next sum is 1/2. So it went from here and jumped back down to 1/2. Then after 1/2, we went to 0.8. So I'll switch colors here. Maybe I'll draw arrows and switch colors. So we went to 0.8, which is 0.83. So it's something like right here-ish, give or take. So we jumped over to here. And then my next term is 0.583. So again, switching colors, 0.58 is somewhere over here, pretty close to 0.6. So it jumps back over to here. And then after that, we have 0.783. So 0.78 is over here. Okay, and then we have 0.616, and that one, maybe we should do in black. 0.616 is over here. Okay, and maybe let's try to understand what's happening. I only did the first 6. If you did the first 10, good on you. That's probably what you should do. What's happening here is that we are jumping past the actual sum. Can you see we're kind of narrowing in on the sum? To me, it looks like the sum is going to be somewhere in the middle here, right? So what happens is, on my first term, I start to the right of the actual sum. And then when I add my next term, which ends up being negative, it jumps us back to the left side of the actual sum. And then the next term jumps us to the right side. And then the next term jumps us to the left side. And so we're bouncing back and forth around the actual sum. This is what we're approaching as a sum. Okay, so we're approaching something here, but we're always, every term always moves us past the actual sum. Hopefully we can see that. Okay, now we're going to go ahead and try to break down the actual sum into smaller pieces. And we're going to break down the actual sum into 2 terms, one of which we've seen before. One is going to be the partial sum, and that is, of course, wherever we stop adding up, right? You can add the first 10 terms, the first 100, the first 1,000,000. Eventually you have to stop adding terms because we can't add an infinite number. That would take a very long time to do. Of course, if you stop somewhere, then that means you've left off some terms at the end. And so it's very commonly referred to as the remainder, which are the terms that we haven't added up yet. So if we added up the first 100 terms, then the remainder would be all of the terms after 100. So it would be the 101st term all the way up to the infinite number of terms. So this is our sum, and this is the stuff that we still need to add on. And so we can sum this up, or we can restate our actual sum as the number of terms we actually add plus the terms we haven't added yet. Of course, we can also manipulate our equation to get a relationship for the remainder just by subtracting the actual sum. And so we can say that the remainder is S minus the partial sum, the actual sum minus the number of terms you've added up. And that, of course, I think should make sense. However, depending on where we end up, we always liked, and you've seen this probably in chemistry before, we always like our error to be positive, our remainder. I just used error there, but sometimes you'll hear that the remainder is called the error. It's how much you're wrong by. Yeah, so if we sum up this number, we're not exactly right. How much are we off by? Well, that's our error. That is our remainder. And we always like that error to be a positive number. So we actually say that the remainder, the absolute value of the remainder, or again, the error, sometimes you'll even see it called E for the error bound. The error is the subtraction of the actual sum minus the number of terms we did in absolute value. Now, let's go ahead and jump back to the number line. Notice that the next term always pushes our sum past the actual sum. So what does that mean here? Well, I jumped over here to my last one. So my next distance is going to, of course, move us to the right somewhere, and it's going to move us, I don't know, somewhere over here. Right? Think about this distance. Let's say that this distance, let's see, 0.6 to, let's say this is 0.72. Let's say that my next term that I add on is 0.1. Well, what do we know about adding on 0.1 to where we started here? Well, if we add it on, it brings us too far, which means if I take my current spot, well, again, I'm calling this 0.62, I think it was 0.7, 0.63, but that's fine. If we add 0.1 onto it, we know our answer is going to be too big. In fact, though, I know that if I add 0.1 and it pushes it by where we're supposed to be, then I know whatever this term is before I add this next term, before I add 0.1, I know that the distance from here to the actual value is less than or equal to 0.1. It's less than or equal to the next term. And for all intents and purposes, really it's less than, because the next term is always going to push us back if it's countable or push us too far. But we say less than or equal because eventually there has to be a term that brings us exactly to the infinite term. But yeah, whatever the next term is will always push you too far. So what we can say is that the amount we're wrong by, the error, has to be less than the next thing that we're adding. And that's really, really powerful. So I'm going to try to put this in a little bit more of a specific mathematical sense. So the next term, and a lot of times I will call this the next neglected term, because it's the term we left off with, so the next neglected term, will always push the current sum past the actual sum. If you're adding, it'll push it above or to the right of the actual sum. If you're subtracting, it'll bring it below or to the left. So that means instead of dealing with the vague remainder r sub n, which is an infinite number of terms that we didn't write, we can say that the actual value of an alternating series, S, right? We can relate the actual value to the sum after n partial sums using the next neglected term, which a lot of times we'll say it's the a sub n plus 1 term. Now that's a lot of complicatedness, so let's see what we mean. S sub n. This is the point that I left off on, and I think the point that I left off on was right here. So let's call this S sub n. This is the partial sum when I gave up writing terms. I was like, I'm done with this. We've done 6 terms, 7 terms, whatever it might be. I'm done writing that. That is my S sub n. And normally you would have to add every single and infinite number of terms that we didn't write to get the exact sum. Well, we know, though, that instead of that, if I take S sub n and just add one more term, if I just add the very next term, should have done that in red. If I just add the very next term, that's going to bring me too far. That's going to be too much. And so what we can say is that the number of terms we wrote plus just one more is going to be too big. Right? It's going to take us past the sum. And we put this in absolute value because that way, in case you subtract something, it turns it positive again and it still works out. So therefore, we can get a better idea of the remainder for the actual value that we add to the sum, the partial sum we wrote to get to the actual sum. We know that this term is bigger than the remainder because, and again, showing you a visual here, I'm adding one term to get over here. So this red line is representing just adding on the very next term value. However, the exact remainder is this distance right here. This is the exact remainder. If I add up an infinite number of terms that I didn't write, then these two added to each other gives us exactly that. But again, I know if I add a sub n plus 1, it's too far. And the advantage of doing that, even though it is too far, is it's not that far, right? It's point something. And the remainder is an infinite number of terms. There's no way I'm going to write an infinite number of terms. I'm just adding one term and we get an idea. And we can definitely convince you that that one term in red up here is bigger than whatever the remainder is. So, in plain terms then, the remainder of the alternating series is always less than or equal, right? And I'm just swapping this around right now. I'm saying that the remainder, the amount that we're wrong by, the error that we're off by, is always less than or equal to the next neglected term in a partial sum. In fact, we say the remainder of the series is bounded because the remainder is always less than the next term by the absolute value of a sub n plus 1, which is the alternating series error, which is like remainder, bound. Now, how does this actually work? You will need a calculator for this part and definitely for a bit of your assignment too. We're going to find the fourth partial sum for the alternating harmonic series in part A. So alternating harmonic series, the fourth up to the fourth term is 1 minus 1/2. That's the second term, third term, fourth term. Cool. And I think we actually did that on Desmos too. So let's keep that going since it's here. I think that's going to be our 0.5833, isn't it? 0.5833. 0.5833. Cool. Well, what's the maximum amount that the partial sum S sub 4 differs from the actual sum of the alternating harmonic series? Now, it's not saying find the actual sum. It is possible to find the actual sum. But it says what's the maximum amount that it differs? So how close is 0.5833? And I mean, looking at my graph up here, here is 0.5833. How close is that to the sum? Well, I actually don't know. But I know the most that I can be wrong by. The most that it could absolutely be is the next term. Well, what's the next term that I didn't write here? The next term, not S sub 4 or S sub 5. The next term that I didn't write is the fifth term. And the fifth term in absolute value, because it doesn't matter if it's going above or below. In this case, it's going above, so it'll stay positive. But the fifth term is just 1/5, which means the most that I am off by here is, and this is 0.2 in case you were curious, is 0.2, right? So this is the largest that I could be off by. Now, technically, if you didn't know what was happening here, you could say that 0.5833 minus 0.2, right? So that would be 0.03833, and 0.5833 plus 0.2, which is 0.7833, you are 100% confident that the actual sum of the alternating harmonic series falls between those two, right? Because that's within 0.2 of this above and below. Because we have my beautiful drawing up here, we know that this is 0.5833 and the next term is this green one, and it brought us over here. That brought us above. So I can actually even narrow it further if I wanted. I could really say that the actual sum is between 0.5833 and 0.7833, just because of that 0.2, the next neglected term. All right, what about part C? What's the maximum amount that the partial sum S sub 13 differs from the actual sum? So if you summed up through the 13th term, well, the most it's going to differ by then is the 14th term, right? A sub 14. It's the next term that we haven't summed up. And this is really easy. The 14th term, well, notice the fifth term was positive. So the 14th term, it's an even, is going to have to be negative here, or it ends up being positive anyway, so it really doesn't matter. So the most that we're actually off by is 1/14. That is the largest that we could be off by, because what's going to happen next is we're going to add, or rather subtract in this case, 1/14 from here, and it's going to move us past the sum. It's going to jump us down below the sum, because every single time you add the next neglected term, it takes you too far. So it has to be inside of that 1/14 value. Now, an interesting one. How many terms are required to approximate the alternating harmonic series with a maximum error of less than 10 to the negative sixth? And in case you're curious, 10 to the negative sixth, I'll need some help here. 10 to the first is 10, times a second 10, third 10, fourth 10, fifth 10, sixth 10, right? So that is 1/1,000,000th. So that, to me, is extremely close. How many terms do we have to add up in order to get a sum that is within 1/1,000,000th of the actual value? That's really freaking close. A tolerance of 1/1,000,000th is essentially the same. Well, how do we do that? The way I like to do it is I like to find the actual term number that creates this from the alternating harmonic series. So I'm going to start with this guy. But because it's the absolute value, all I'm really going to deal with is just 1/n. So my question is, what do I have to plug in for n to get an answer of 1/1,000,000th? Well, hopefully we can see that n has to be 1,000,000. Now, we need to be careful, because if we add up the first million terms in the alternating harmonic series, we're not going to be off by an error less than that, right? In fact, if we add up the millionth terms, whatever that is, the amount that we're off by is actually the term after that. So the n plus first term, right? The next neglected term after those million terms is actually this, right? That's the next term. And so this is going to make me a million terms in, right? And the error that I'm off by is this guy. And that's okay, because that is certainly less than 10 to the negative 6. A bigger denominator, it's a smaller fraction. But what if I added up the 999,999 terms, the first of all those? Well, then my error, and I'll keep doing this in red, the n plus first term would be 1 over 1 million. The next term that I didn't write is this term right here, right? We take this, we just plug in the value. So this would be off by at most 1/1,000,000th. So do I want 999,999 terms, or do I want this? Well, the problem said we want a maximum error strictly less than 10 to the negative 6th. This is an error of possibly equal to 10 to the negative 6th. We wanted less than that, so we actually need this guy. We want a million terms added up so that the error will be less than 1/1,000,000th. By the way, in case you were curious, the alternating harmonic series is exactly equal to the natural log of 2. That is wild to me, right? The fact that we can take something that looks like this and say, oh, by the way, that's the natural log. What? How is that natural log of 2, which is a gross number? You can try it on your calculator. If you plug in natural log of 2, you're going to get a decimal, and guess what? The decimal is going to be in between these two. We will actually talk about why in our next unit, but that's not now. Very last problem. The series below converges to some sum s. Based on the alternating series error bound, what is the fewest, I should say fewest here, not least. Least is, we can count this. The fewest number of terms in the series that must be summed to guarantee a partial sum that is within 0.03 of the actual sum. Well, this is the error tolerance that they're giving us here. So we're going to do the same thing. We're going to strip out the absolute value. We don't care about that. And we're going to say, okay, well, what makes, and I'll work over here, 1 divided by the square root of n equal to exactly 0.03? Well, I would be super clever here, and I would just say 1 divided by the square root of n, has to be equal to 3 100ths. This is 3 100ths, isn't it? Okay. And then let's start solving. So I'm going to flip both of these. So square root of n over 1 equals 100 over 3. I don't really even need the over 1, right? Reciprocal of each. Then I think we just have to square both of them. And so that tells me that n is going to be 100 divided by 3 squared. Now, what is that actually? I don't know. We should probably go out and use our calculator here. So we have the fraction, wherever that went, there we go, 100 over 3, and we want to make sure all of this is squared. It's going to give me a fraction, so I'm going to copy this guy down and say, please give me a decimal kind calculator. 1111.11. I can do that. So 1111.11. Well, what did we find here? This tells me if I use, so this is going to be term number 1111.11 will give me an exact value of 0.03. That's what I just solved for right here. Now, that's awesome, but they asked us to guarantee a partial sum that's within this. So we want to be less than, and I did an extra 0 here, we want to be less than 0.03. Well, how do we be less than that? Well, this isn't actually a specific term number. So let's try to think about what happens if we either go down or up to the next term number. Let's say that I use term n equals 1111. Let's actually say that I find the partial sum of the first 1,111 terms. Well, then my error, right, my error here will be the next term, and the next term is 1 over the square root of 1112. Right? That's the next term that I didn't use if I add up the first, 1,111. The next term I didn't use is this. Well, if this in between these two values gives me exactly this, then a term that's further along than this, right, 0.89 higher than that, is going to give me a value that is less than 0.03, right? The same way that if I used exactly this term, this would give me a value that's greater than 0.03, because this is exactly 0.03, so one smaller term would be greater, one larger term would be smaller. And so that's actually what I want. I want to find something that's less than that, so that means I want to sum up the first 1,111, and that means that my error will be exactly this, which is less than 0.03. Now, of course, on this problem, you didn't really have to differentiate between what if it's this versus that, but it's always good to think about. Your assignment tonight has the alternating series test on, on the first few, and then the last four are all about the alternating series error bound. Thank you for your hard work. You only have one lesson left, and then we'll get some reviewing, and finally we can get to our final topic here, the best one, power series. However, next class is a little bit more on our infinite series, and then we of course have our test before we get to the coolest topic of the semester, or possibly the year, or possibly the 2 years. Thanks for sticking with me.